Okay, we are going to continue with topic 14 on acid-base equilibrium by focusing on section 4 of the notes. This is on buffer solutions. So before that, we need to look at the definition of a buffer. Okay, so as written on the notes, the buffer solution is able to resist pH change when a small amount of acid or bases is added. Take note that this must be a small amount. So, well, I mean, how small depends on the strength of your buffer as well. Yeah, so in most cases, that will be about, say, 5 to 10%. Okay, but I think it will be clearer when we perform calculations later on. Okay, and normally when we are talking about the acid and base here, we are really talking about a pure H3O plus, meaning a strong acid, and for bases will be a pure OH minus being added. Yeah, later on I think it will be clearer as well. Okay, so basically a buffer resists pH change, or you can say that it causes negligible change in pH. A common misconception is that buffer will not result in any pH change. This is incorrect. Okay, so the keyword is resist, or another way to discuss it would be results in negligible pH changes when a small amount of acid or base is added. Okay, another thing you might want to take note of for a buffer solution is that it usually consists of a conjugate acid-base pair of a weak acid or base. Yeah, so let me just give you two simple examples. So when we talk about an acid buffer or an acidic buffer, so for example acid buffer, I think you should be able to tell that the acid buffer should contain ethanoic acid being the weak acid, okay, and its corresponding conjugate base or salt. So in this case it will be ethanoate. Okay, and then for a basic buffer or an alkaline buffer, what you are familiar with would be aqueous ammonia. Okay, and of course its corresponding salts or conjugate acids, in this case ammonium. Yeah, but do take note that whenever we say the corresponding salts, we really don't mean that you can simply just add ethanoate or in this case ammonium. Okay, so the salts will be added for the case of ethanoate in the form of sodium ethanoate, and of course for to create the basic buffer with ammonia, we'll be adding aqueous ammonia as well as a substantial amount of ammonium chloride. Okay, so you will learn more about it later on. Yeah, but just for you to take note that in order to create or produce a buffer, the two species involved must be a conjugate acid-base pair. So that means that the difference between the two species must be by a H+. Yeah, so that is very important. Okay, so with that, we will move on to exercise 4.1. And for the first question, you are being asked whether the following mixture can act as a buffer solution. Okay, so I think a very simple way of looking at it would be, first of all, we have sodium bicarbonate and we have sodium carbonate. So let us take a look at the cation. So Na plus obviously will not undergo any form of hydrolysis in water, so it will simply be the spectator ions. So we will not be focusing our attention on Na plus. And then we are looking at hydrogen carbonate, or otherwise known as bicarbonate. And then we are looking at carbonate itself. So we have CO3 2 minus. So you notice that the difference between the two is actually a H+. So if I draw an equilibrium arrow, then bicarbonate will ionize partially to give me carbonates and H+. So you can see that the difference between them is really a H+. So in that case, I expect bicarbonate or hydrogen carbonate and carbonate combination, they can form a buffer solution. So this will be yes. Okay, so the first question would be yes. Okay, for the second question, we have ethanoic acid and sodium chloride. So ethanoic acid is a weak acid, and of course sodium chloride is not conjugate base of ethanoic acid. Yeah, so this is just a random mixture. So I will not expect it to be a buffer solution. So I will give it a no. And then for the third option, you have nitric acid. So nitric acid is actually a strong acid. And then we have sodium nitrate. For sodium nitrate, nitrate will be the conjugate base of a strong acid. So it will not hydrolyze appreciably in water. So in that case, nitric acid and sodium nitrate will not make up a buffer solution. So the answer will be no. Yeah, remember that a buffer solution, right? The acid and its corresponding salts, as well as for a basic buffer, the base and its corresponding salts, their combination must be weak acid and a weak conjugate base. And then for the basic buffer, a weak base and a weak conjugate acid. Yeah, so if you start off with a strong acid, then your corresponding conjugate base will be a very, very weak base. So in the case of nitric acid, the nitrate is a very, very weak conjugate base. So this combination will not result in a buffer solution. Okay, so that is something you need to pay attention to. And then moving on to 4.2, where we are supposed to prepare a buffer solution. So we can just go through this a little bit so that you are familiar with the mechanics of how a buffer is being produced. Okay, so we have a buffer solution containing a weak acid and its corresponding conjugate base. Okay, and first of all, you need to understand that the weak acid will ionize partially to give me ethanoate and H+. Okay, so this is a partial ionization. Okay, and then if you artificially add sodium nitrate into the above solution, okay, then you results in two things. There are two things that will happen at the end of the day. First thing is sodium ethanoate is expected to be very soluble in water because number one, sodium salts are very soluble in water. Okay, so that's why we have this qualifier completely dissolved in water. So once you dump in sodium ethanoate, you are supplying the solutions. Okay, when I mean you dumped in sodium ethanoate, you are dumping it into the ethanoic acid solution. Okay, the solution will contain a lot of sodium plus and ethanoic anion because it's a complete dissolution. Okay, and when that happens, you might notice that it will actually suppresses the ionization of ethanoic acid. Okay, so this is according to what you learn from the Le Chartier's principle in chemical equilibrium. Okay, so if you are still unsure, just let me repeat myself again. So first of all, we have ethanoic acid ionizes partially in water to give me ethanoate and H+. Okay, so this is a partial ionization. Okay, and then to this particular solution, I added in sodium ethanoate, which is completely soluble in water. And in that brief instance, I will introduce ethanoate in a huge amount. I will introduce a huge amount of ethanoate into the solution. So this will result in the suppression in the ionization of ethanoic acid. Or another way to put it would be the position of equilibrium of one will shift to the left. Yeah. Why is this important? I mean, some of you will be a little bit puzzled at this instance. Like when you mention this, yeah. So what is the outcome? Okay, so the outcome is that number one, I will have a large reservoir of ethanoic acid, and then I will also have a large reservoir of ethanoate anion because I've added them in artificially. And then the combination of these two, meaning the combination of ethanoic acids as well as its conjugate base or the salts. Okay, so this combination will result in a buffer solution. Okay, so take note that we have not explained how the solution acts as a buffer at this stage. Yeah, we are just telling you the mechanics of producing a buffer solution. Okay, so to explain how the buffer solution works, we'll move into it later on. Okay, and then mixing a weak base and its conjugate acid. This is the same scenario. Okay, so earlier on, we are producing an acidic buffer. Okay, so maybe I should put notes here. So this is producing an acidic buffer. Okay, so this is very important. Some of you might be wondering, I mean, if I may just clear the doubts at this stage. Since ethanoic acid is a weak acid and ethanoate itself is a weak base, why is the overall solution an acidic buffer instead of a basic buffer? I mean, some of you might ask this question. Actually, I've addressed it in the earlier part of the topic, but I can talk about it again. Okay, so it all boils down to the pKa value. So the pKa of ethanoic acids is 4.76. I think it will be good to remember this because ethanoic acid is really the benchmark we often used for H2 chemistry, even for undergraduate chemistry as well. And if you know the pKa value of ethanoic acid, you can easily tell me and calculate the pKb value of ethanoate. So it will be 14 minus 4.76, that will be 9.24. Okay, yep. And then you might also be aware that the lower the pKa and the lower the pKb value, the stronger the acid and the base. Yeah. So you notice that the pKa value of ethanoic acid is lower than the pKb value of ethanoate. So that means that ethanoic acid, it will function as a stronger acid as compared to ethanoate functioning as a base. Yeah. So in that case, what we are saying is that when we mix ethanoic acid and ethanoate together, the extent of ionization of ethanoic acid will dominate a little bit more. Okay, and with this, I think you should be able to understand why is the mixture of a weak base and its corresponding conjugate acid, why will it produce a alkaline buffer? So this will produce an alkaline buffer. Okay, or you can just call it a basic buffer as well. Okay, so when you combine the two, you're going to get a basic buffer, and I think we can look at it in a similar fashion as ethanoic acid. So first we have aqueous ammonia, being a weak acid which ionizes partially. So that's over here. So it ionizes partially to give me the conjugate acid, which is ammonium and OH minus. And then when I add in artificially ammonium chloride, which is completely soluble, the extra ammonium ion, okay, will cause the position of equilibrium of 2 to shift to the right, to shift to the left. Okay, so results in POE of 2 to shift left when we add in ammonium. Okay, then so in that case, I will have a large amount of unionized ammonia as well as a large amount of ammonium ion. And then this combination will actually give me a buffer solution. And then how do we know whether it will be an alkaline or acidic buffer? I think I've mentioned earlier on, we need to look at the pKb and the pKa value of the base, in this case ammonia, and as well as its corresponding conjugate acid, and then we compare which is lower, and then the lower one will predominate. Okay, and then okay, so let us move on to this partial neutralization of a weak acid or a weak base. Okay, so usually students will be a bit confused when we reach this stage. So maybe before that, let me just recap a little bit. Okay, so first of all, right, how do we actually produce buffer? Okay, so maybe I'll just use the small space here to write down. So we can produce, let's say I want an acidic buffer. Okay, so we need the weak acids. Okay, and then we can artificially add in the salts. Okay, like what we did just now for ethanoic acid, and then we just add in solid sodium ethanoate. Okay, now those of you who are sharp enough, right, you probably realize that actually I do not really need to artificially add in the salts because I can actually start off with a weak acid. Okay, and then I just add in maybe some amount of sodium hydroxide, and then the weak acid will undergo acid-base neutralization reaction with the OH minus, and in that case it will produce ethanoate anion, and the combination of the ethanoate and the remaining amount of ethanoic acid, that is also a buffer. Yeah, so yes, this is one way. So in this case we can have weak acid plus some amounts of NaOH. Yeah, so this is the portion we are actually trying to discuss in 4.2.3. So that is what we call a partial neutralization of a weak acid. Okay, or in that case for a weak base. So in that case, let's say we want to make an alkali buffer from aqueous ammonia. We need not add ammonium chloride to aqueous ammonia. What we can do is we will partially neutralize aqueous ammonia with a strong acid such as hydrochloric acid. Okay, but do take note that you do not neutralize it too much. Yeah, don't add beyond a certain limit so later on you're going to learn that there is a limit for the buffer which can work well in order to resist change in pH. Yeah, because if the corresponding salts and the acids or base, if they differ by too much a number, then it will not act as a good buffer. Yeah, so that's also something which you will be introduced later on. Yeah, and the partial neutralization portion is particularly important when we are talking about titration curve, and that is often the points where the students will get very confused. Okay, so this portion you can KIV till section 5. Okay, then we'll move on to an exercise 4.2 where you'll be asked to pick the combination of substance when you mix them that will not give you a buffer. Okay, so we can do it quite quickly. We just need to see what we have. Okay, so first we have a strong acid. Okay, 25 cubic centimeters of 0.1 molar HCl. And then we also have 0.1 molar of aqueous ammonia. Okay, but the aqueous ammonia, of course, is double the volume. Yeah, so that means that for combination A, right, you would expect to have about the same. I mean, you expect molecular ammonia and the ammonium form to be of similar amounts. Yeah, because the amount of hydrochloric acid added in terms of number of moles is half that of the amount of aqueous ammonia present. Okay, so in that case, I expect to produce a substantial amount of ammonium, and then and the amount of ammonia remaining in the solution is also quite substantial. So this combination, you would expect it to be a buffer. Okay, so this will be a buffer. Okay, so I'm going to write it down. I'm going to expect this to be a buffer solution. And then for combination B, I have sodium hydroxide, 25 cubic centimeters, 0.1 molar, and then I'm adding it to 25 cubic centimeters by 0.2 molar of ammonium. Okay, so the concentration of ammonium is twice that of sodium hydroxide. So again, I'm going to produce a substantial amount of ammonia in the process, but there is still a substantial amount of ammonium left behind. If you are sharp enough, you can tell that this is also sort of like a 1-to-1 ratio. So this will also be a buffer. Okay, if you need to perform the calculation, please do that. If not, you can just look through the options and then decides on which is the correct option to pick. Okay, so next we have 0.2 moles per dm cube, or 0.2 molar of HCl, 25 cubic centimeters, and then we have 0.1 moles per dm cube of ethanoate. Yeah, so you notice that when I add in HCl to attenuate, right, the hydrochloric acid will be in excess. Yeah, and then so in option C, right, what I'm going to get is simply attenuate acids. I'm going to get attenuate acids swimming around, swimming in a large amount of H+. The large amount of H+ actually comes from the unreacted HCl. And then this is obviously not a buffer because the attenuate acid do not have its corresponding conjugate base, in this case attenuate, present. Yeah, so therefore option C will be the one I'm going to pick for 4.2 because this is not a buffer solution. Okay, but as per all MCQ, I think it's good to also look at the other option, which is option D. So we have 0.1 molar of sodium hydroxide added to 0.2 molar of attenuate acid. So similar to option B, there will be, when all the sodium hydroxide reacted, there will be a substantial amount of attenuate being formed and also a substantial amount of attenuate acid remaining in the solution. Yeah, so this will create a buffer solution. Yeah, so D is also a buffer. Yeah, so option C is the one I'll pick because it will not be a buffer, as what I've explained earlier on. It doesn't have the conjugate base in presence with attenuate acids. Okay, so moving on to 4.3, when we are trying to explain the buffer action. Okay, so maybe before I discuss this, I thought it will be interesting for me to maybe just use the blank space here to explain a little bit about how a buffer actually works. I mean, without going into 4.3 first. Okay, so I will be discussing attenuate acid buffer. Okay, so we have attenuate acids and we have attenuates. So I just put a comma, attenuates. Okay, and then I will be using an equilibrium expression to help me in my explanation. So so this equilibrium solely refer to attenuate acid. Okay, so so that you guys don't get confused. So this solely refer to attenuate acids. Okay, so I will have H plus, CH3, CO2 minus, and then as well as attenuate acids equilibrium amounts. Okay, yep, and you might recall from earlier chemical equilibrium that when we add in attenuates, it will suppress the ionization of attenuate acid. Okay, so maybe I should write this out so that you can see it in a clearer fashion. This equilibrate to give me attenuates, okay, and H plus. Yeah, so the addition of attenuates, in this case attenuate as sodium attenuate, will actually suppress the ionization of attenuate acid, right? But there is still an equilibrium amount of attenuate acid and attenuate present, although the ionization is being suppressed. So therefore, this expression will still hold. Okay, except that the H plus and attenuate is no longer in a 1:1 ratio because I artificially added in a substantial amount of attenuates. Okay, so in that case, right, I hope you do recognize that therefore the ratio of attenuate to attenuate acid is important in determining how good the buffer is. Okay, because from here you are able to calculate the change in the amount of attenuate and attenuate acid, and in the process you can determine the pH of the solution. Okay, so I'll just give you a very rough view about what exactly is happening, so that later on when we perform the calculations, it will be clearer. Okay, so if you are still in doubt, you might want to pause here for a little while and then think about what I've just said. Yeah, if not, I'm just going to move on with my explanation. Okay, so suppose I give you the pKa of attenuate acid. So the pKa of ethanoic acid is 4.76. Okay. So you will be able to calculate the Ka quite easily. So that will be 10 to the power minus 4.76. Yeah. And as what we have learned in chemical equilibrium, this is a fixed number. Yeah, this is a fixed value. It's only temperature dependent. Yeah. So let's not worry too much about this. Okay. So and also suppose that in my solutions, I have the same amount of ethanoic as well as ethanoic acid. Okay, so let's say so I'm going to give you this scenario lah. So in 1 dm cube, okay, the amounts of ethanoic acids equals the amounts of ethanoics. And then I will just give a random number. So let's say is 0.200 moles. Okay, then you'll notice a very interesting phenomenon. Okay, because the amounts of ethanoics is the same as the amount of ethanoic acids. So that means that the ethanoics present, right, will suppress the ionization of ethanoic acid. So that means that despite adding these two amounts, or rather despite adding 0.2 moles of ethanoic acid and ethanoic into the solution, each of them will not ionize or hydrolyze to a significant extent. Yeah. So therefore, at equilibrium, you can approximate the amount remaining in the solution to 0.2 as well. Okay, so I mean, as I mentioned earlier on, because the reason is I know that some ethanoic acid will ionize to ethanoate, but once you add in ethanoate, it will suppress the ionization so that you can use the amount of ethanoic acid present as a proxy to the amount that is present in the buffer solution. And of course, when you add in sodium ethanoate, you expect the ethanoate to hydrolyze to give you ethanoic acid and OH minus. Yeah, but because of the presence of ethanoic acid, you don't expect ethanoate to hydrolyze to a significant extent. Yeah, so therefore the amounts of ethanoic acid and ethanoates, you can approximate them to the same amount which you have added at the start. Yeah, so that will make your calculation very straightforward. I don't know whether you realize it. Yeah, because that will mean that I can then easily calculate the pH of this particular buffer with the same amount of ethanoic acid and ethanoate. Okay, how do I do that? Okay, you know the pKa, right? So the pK is 10 to the power minus 4.76. Okay, and then you know the concentration of H+, which you're supposed to calculate. I mean, sorry, you don't know, so you're supposed to calculate. Yeah, and then what is the concentration of ethanoate? So the number of moles is 0.200. So this divided by 1.0 because I'm talking about 1 dm cube over here. And then divide by 0.200 divided by 1.0. Okay, so you realize that I can actually cancel these two terms. And therefore, the concentration of H+ will be this number. And then I can easily determine pH. I just punch my calculator. I should get 4.76. Yeah. Okay. So you notice that when the amounts of the weak acid and the salt is the same, the pH equals to the pKa. That is something which you will encounter later on when we are discussing titration curve. Okay, now I know that it might be a little bit too early to introduce this, but I just thought that I can just briefly bring you through the mathematics so that you have a clearer picture on what is going to happen later on. Okay, and then now I'm going to just do a small thought experiment. Okay, so I know it's a bit messy. Okay, so I'm just going to move on to the left hand side. I'm just going to use the little bit of space I have over here to complete the calculation. So suppose I add in 0.050 moles of H+. Okay, so suppose I add in 0.050 moles of H+. Okay, to this solution. Okay, to this particular solution. Okay, then regardless, okay, so assume that the volume is negligible, but it doesn't really matter, which you will realize later on. Okay, now what exactly is going to happen? Okay, so when I add in my H plus, the question to ask yourself is which of these two species, ethanoic acid or ethanoate, will react with the H plus being added? Yeah, so I think the answer is obvious, because ethanoic acid is a weak acid, ethanoate is a weak base, so of course the base will react with the acid, right? Yeah, so in that case, I expect ethanoates to react with the acids. So so the ethanoates will undergo an acid-base neutralization reaction in a 1:1 ratio, and it will react with the H plus being added completely. So whatever H plus I've added, so the ethanoate will react with it. So because they react in a 1:1 ratio, so I can easily calculate the amount of ethanoate remaining after the reactions. Remember that I started off with 0.200, so the amount of ethanoate remaining will then be 0.200 minus 0.050, so that will be 0.150 moles. Okay, then after that, I can determine the amount of ethanoic acid remaining as well. So because ethanoate and H plus react in a 1:1 ratio, yeah, so whatever amount of ethanoate being consumed to react with H plus, okay, will result in the formation of ethanoic acid. So therefore, the number of moles of ethanoic acid will be increased to 0.250. So this will be equals to 0.250. Okay, so with that, can we now calculate the pH of the final solution? Okay, so we can do that. How do we do that? We use the same logic. So 10 to the power of 4.76. Remember Ka expression. H plus. Okay, and then now the amount of ethanoates is 0.150. Okay, and then it will be 1.0, so that is the initial volume. Because I've added in H plus from an unknown volume, I can just plus V naught. It doesn't matter what is V naught, okay, and then divide by 0.250 over 1.0 plus V naught. You realize that it doesn't matter what the V naught is, because it will be cancelled out. Okay, and if I were to punch my calculator from here, right, I will be able to get a H plus concentration. So let me just punch the calculator. So 10.15 divided by 0.25, that gives me 0.6. Okay, so 10 to the power of 4.76 divided by 0.6. So the concentration of H plus will now be 5.779 times 1, 2, 3, 4, 5. 10 to the power of minus 5 moles per dm cube. So from here, I can determine the pH simply by just taking the negative log of the concentration of H plus, and I will get 4.24. Okay, now do you notice that the pH reduces from 4.76 to 4.24? Yeah, this is quite a substantial drop, but not substantial enough until it goes from like 4.76 to 1. Okay, and the reason why the drop is relatively substantial is because I purposely added in quite a huge amount of H plus. So that is like 1/4 the amount of ethanoic acid or ethanoate present. So because I do that, you realize that the pH actually drops by 0.52. But it still holds on to pH quite well, if you notice. Like, yeah, as I said, the drop is not from like 4.76 to 2 point something or 1 point something. It's only a drop of about 0.5. Yeah, so that actually proved to you how the buffer actually works. Like, because of the combined action of both the weak acid and its corresponding salt. If in case you might be wondering if the solution is not a buffer, what is going to happen? Okay, so we can easily do that by mathematics. So let's say you add in 0.05 moles of H plus to 1 dm cube. Okay, so therefore the concentration of H plus would be 0.050 moles per dm cube, right? So you can easily determine the pH from here. So we can easily take a negative log of 0.05, and then you get a pH of 1.30. Yeah, so if I add in 0.50 moles of H plus to 1 dm cube of water, my pH is 1.3. But if I add in to a buffer solution, okay, originally the pH is 4.76, it only drops to 4.24, so it's a 0.52 drop. Yeah, but if I add into pure water, the drop is from 7.00 to 1.30, so that's a drastic drop. Yeah, so I hope this little exercise, not exactly exercise, but this little explanation provide you with a glimpse on how buffer works. Although you might not be very clear at this stage, because I guess there are still quite a number of unanswered questions, but I think it doesn't really matter because you can always review them again along the way. Okay, yeah, so I think I have jumpstart this, but maybe we can go through this portion of the notes relatively quickly. So we have 4.3 where you are required to explain the buffer action. Yeah, so again, first of all, when we have a buffer, same example, a large reservoir of ethanoic acid and conjugate base, so similar to what we have earlier on, which is 0.200. Okay, what will happen when we add in a small amount of acid? So again, the H plus reacts with ethanoids, which is the conjugate base, through this acid-base neutralization reaction. Okay, and what happens after that? Okay, so over here, they did not give you any numbers, so they just say that the amount of ethanoic acid increases slightly, this decreases slightly. Yeah, but this will be the same amount as what we shown you earlier on. So I think if I plug in some numbers, it helps, and that is the reason why I was just trying to explain or jumpstart the explanation of section 4.3 without going through the words, giving you some numbers first to appreciate. Okay, so we can say that this particular ratio remains relatively constant, so therefore the H plus will remain relatively constant. But of course, if the amount is quite significant, then the ratio will change relatively substantially, and then the pH will change, but it will not be a drastic change like when you add 0.05 moles of H plus to pure water. Okay, and then of course, when a small amount of OH minus is added, the same thing happens. I didn't show you the OH minus example earlier on, but you can do the same mathematics on your own. Okay, and then yeah, so the explanation is the same. In this case, when OH minus is added, the weak acid will react with the base, in this case OH minus, and in the process it will produce ethanoate and H2O. Okay, so again, this ratio remain relatively constant, and H plus and pH will remain relatively constant. Okay, a very important thing you might want to take note of, which I might not have emphasized, is that for buffer actions, the equations are non-reversible, because we are really talking about a complete reaction between the added strong acid and strong base with the corresponding conjugate base and weak acids. Yeah, so we are really talking about that particular reactions. We are focusing on that, so therefore it's an irreversible error. Okay, so now let us look at exercise 4.3. How does a buffer solution containing ammonia and ammonium chloride resist change in pH when small amount of acid or alkaline is added? So again, we will discuss the same logic. Okay, so first of all, right, we have a large reservoir of ammonia, okay, and a large reservoir of ammonium, which is NH4+. Okay, so when a small amount of acid is added, okay, so when acid is added, it will react with ammonia, so H plus ammonia, then we will get ammonium. Okay, so this is when small amount of acid is added, H plus added, Okay, so when a small amount of base is added, small amount of OH minus, so the OH minus will react with the substantial amount of ammonium present, and in the process give us H2O and ammonia. Okay, ammonia. Yep, and as what we have seen earlier on, so before we discuss, we need to write a Kb expression for aqueous ammonia. So therefore, it will involve ammonium over here and OH minus, and then NH3. Okay, and I'm going to highlight the constant term. So Kb will be a constant because it's a temperature dependent variable. Yeah. So how the pH will change depends on the ratio of ammonium and ammonia, as what I have illustrated earlier on using the ethanoic acid buffer example. Yeah. So in our case here, because the amount of H plus and the amount of OH minus added in separate situation, I think maybe I should emphasize that over here, right, they are talking about in separate situation, in separate solution. So you don't add acid and alkaline to the same solution because that doesn't make sense. Okay, you are adding them to separate solutions. Okay, so these are separate scenarios. So this is one scenario, and this is the other scenario. Okay, so these are separate scenarios. Okay, then the ratio of ammonium, okay, and ammonia will not change appreciably because the amount of ammonia and ammonium is large as compared to the amount of H plus and OH minus being added. And because of that, I don't expect the ratio of ammonium to ammonia to change appreciably. So therefore, the amount of OH minus in the solution remains relatively constant. So therefore, the pH remain relatively constant, or you can say relatively invariant. Yeah, but this is just a very qualitative kind of answer. The actual calculation which you should have done when you are given a calculation question, you should have done some calculation to verify that the pH will change slightly, but not in a large fashion. So I think I have, as I said, I think I repeated myself too often. I have shown you an example over here using the ethanoic acid ethanoic buffer. So I hope this can help you to appreciate the actions of buffer a little bit more beyond qualitative aspect. Yeah, the quantitative aspect, the calculation part will only come in later on, which we are looking at next at section 4.4. Okay, so I think I have already introduced you to some of the mathematics. Yeah, we can discuss this. So yeah, so we have a buffer consists of the weak acids and the corresponding conjugate base. You have this equilibrium expression. Okay, and as I mentioned earlier on, because I'm adding the conjugate base in similar amounts to the amount of the acid present, I do not expect the weak acid, in this case HA, to ionize substantially. Okay, so the presence of A minus in this case will suppress the ionization of HA. So therefore, the amount of HA at equilibrium is similar to the amount of HA I have initially, and the amount of A minus I have at equilibrium is similar to the amount of A minus I've added into the solutions. Okay, so therefore we are really looking at the ratio of the acid and the conjugate base for an acidic buffer. Okay, and I hope you are able to understand why H plus is not the same as A minus. If you are in doubt, again, please refer to the earlier portion of the video, or check out on your understanding of chemical equilibrium from the earlier topic on chemical equilibrium. Okay, and there is a expression which you can actually derive from here. So from this particular expression, if you take a minus log base 10 on both sides, you are going to end up with this particular expression. Okay, so pH equals to pK plus log base 10, the ratio of conjugate base over acid. This is known as the Henderson-Hasselbalch equation, which some people call it the buffer equation, and you can use it to calculate the pH of buffer quite easily. Yeah, but take note that when I highlight this, I do not mean you have to memorize this expression. Yeah, so there isn't a need to commit this expression to memory for a very simple reason, because if you do not like to use this expression, you can simply fall back onto the Ka expression and you can still calculate the pH. Okay, like what I did earlier on. Yeah, can you see over here, I did not use the Henderson-Hasselbalch equation. I simply just used the Ka expression. I calculated the concentration of H plus and then I determined the pH. Yeah, so it can be done quite easily. Okay, but of course, if you wish to, you can remember this, or after you have worked quickly, sometimes you can easily derive this expression at your own will during exam, and then you can easily use that to your advantage. Okay, again, I do not encourage students to commit these to memory. We are just showing you this expression to just impress upon you that you can easily derive them for your own use for assessment purposes. Yeah, if you don't wish to, you can just use the KB expression to solve. Okay, we will look at exercise 4.4 now, where you are supposed to calculate the pH of a solution containing 0.1 mole of ethanoic acid and 0.01 moles of ethanoic acid and 0.010 moles of sodium ethanoate dissolved in 1 dm³ of water. And I don't think you need me to go through this example because I have shown you the mathematics in my illustration over here. Okay, so what you can do is simply just for complete, just to ensure that I complete all exercises. So I'll just do that quite quickly. So therefore, my Ka expression, I will equate it to H plus and then ethanoates, okay, and divide by ethanoic acids. And because I have a substantial amount of ethanoic acid and sodium ethanoate, right, I expect the equilibrium amount to be the same as this. And because both amounts are the same, they will cancel out. Okay. It doesn't really matter here because 0.010 divided by the volume term will also cancel out. So K equals to H plus concentration. So 1.8 times 10 to the power minus 5 equals the H plus concentration. So I can easily calculate pH to be 4.74. Okay, yeah, you can easily do that. Yeah, so over here we have a application example. I think it's the same example as what I showed you earlier on. Okay, so we have pure water. I add in sodium hydroxide, 1 cubic centimeters from 1.0 moles per dm³ solution. Okay, so from here, the concentration of OH minus, you can easily determine that will be the number of moles divided by the total volume. So because I added into 1 dm³ solution, so the total volume will be 1001, and then the concentration of OH minus will be 9.99 times 10 to the power minus 4. Okay, I can determine the POH, and then the pH is 11.0. So the change in pH is from 7. Okay, so it will be from 7 to 11.0. So this is a whopping 4-unit change. Okay. Then for the buffer earlier on, which we calculated above, remember that the amount of ethanoic acid is 0.010 and the amount of sodium ethanoate is 0.010 as well. The number of moles of hydroxide added is 0.001, so that's a 10%. Okay, so in that case, the amount of ethanoates, okay, because they react in a 1:1 ratio to produce 1:1, right? So if 0.001 moles of sodium hydroxide is added, the amount of ethanoic acid consumed will be 0.0010. Yeah, so therefore from here you can determine the amount of ethanoic acid remaining, and of course the amount of ethanoate formed will go up by 0.0010 as well, so you add 0.001. So you might notice that whatever amount of ethanoic acid consumed, okay, will also result in whatever amount of ethanoate being formed, and this is often the case. So if you realize this, I think it will be easier for you to work through problems later on. Okay, and then of course we have the K expression. We don't need to use Henderson-Hasselbalch equation, remember? Yeah, you can simply work with the K expression. And then you can determine the H plus concentration and then the pH 4.83. So you notice that the change in pH is simply from 4.74 to 4.83. So the change is 0.09 units. Okay, so from here you can see that if I added in 0.001 mole of sodium hydroxide to pure water solution, 1 dm cube of pure water solution, the pH changes from 7 to 11. But if I add into a buffer containing 0.010 moles per dm cube of sodium, sodium ethanoate and ethanoic acid, the pH changed from 4.74 to 4.83. So it can resist the change in pH a lot better. Yeah. So again, let me just emphasize the reason why I wanted to show you the calculation way before the qualitative aspect is to first bring you into the idea that buffer really resists change in pH, and then later on some qualitative explanation which hopefully can firm up your understanding. And then if you're unsure, you can go back to this, and then later on you can see that we have done some calculations over here, the equations, and then an application example which show you how a buffer resists change in pH. Okay, yeah, remember the word is resist the change in pH. Yeah, the pH will still change at the end of the day. Yeah, that is something you have to recognize. Okay, next we'll move on to buffer capacity. Okay, so I think you can read the paragraph given to you over here. So it reads, the capacity of a buffer is the quantity of H3O plus or OH minus it can remove before its pH changes drastically. Yeah, so without going into further reading, I will just give you an example using what I have illustrated to you earlier on. Yeah, so if you recall earlier on, I used this particular ethanoic acid ethanoic buffer where I have 0.200 moles of each, and then at the end of the day, the concentration of ethanoic acid and ethanoate is 0.200 moles per dm cube. And then after that, I added in 0.050 moles of H plus, and then you'll notice that the pH changed from 4.76 to 4.24. Okay, so I'm just going to summarize this over here. Okay, so just to recap, I have 1 dm cube of ethanoic acids, and ethanoic buffer. Okay, and then the concentration for each of them is equals to 0.200 moles per dm cube. Okay, and then starting pH is equals to 4.76. How do I do that? Well, I mean, I did that simply by using the Ka value, which is 10 to the power of minus 4.76. And then I equate it to the equation H plus then concentration of ethanoates, and then divide by ethanoic acids, and then as what we mentioned earlier on, because the initial concentration is the same, so from this equation you cancel, so therefore pH equals to pKa equals to 4.76. Okay, then after that 0.050 moles of H plus is added. Okay, and then without going to the calculation, the pH reduces from 4.76 to, okay, so I forgot the number, so just need to look back to 4.24. Okay, to 4.24. Over here, yeah, to 4.24. Okay, so right now I'm going to present another scenario to you. So instead of the concentration of ethanoic acid and ethanoate to be 0.200, so what if I start off my concentration of ethanoic acid and ethanoate to be of a higher value? So maybe I'll just randomly pick off the top of my head, maybe 0.500 moles per dm cube. Okay, just a random value. You can start with any values you wish to, but not too concentrated, of course. Okay, the starting pH will still be 4.76. Okay, you can verify it for yourself. The starting pH will still be 4.76. Okay, because it will still satisfy this particular scenario, yeah, where the concentration of ethanoate and ethanoic acid is the same, so they will cancel out. Yeah, so the starting pH remains the same. Yeah, but we'll try with the same number of moles of H plus added, which is 0.050. Okay, so therefore I'm going to work using this equation instead of the Henderson-Hasselbalch equation, just to impress upon you that you don't really need to memorize any equation in order to work through the problems. Okay, so what we have here is 10 to the power minus 4.76. Okay, so this is equals to concentration of H plus. Okay, and then so what is the eventual outcome? So remember, if I add H plus, I will be reacting away the ethanoate present. Okay, so initially I have 0.500 moles of ethanoate in 1 dm cube of solution. So therefore the number of moles of ethanoate, right, will reduce by 0.050. Okay, so 0.050. Okay, the solution volume will be 1.0 plus V. So I don't know what is V, but it doesn't really matter. Okay, and then the amount of ethanoic acid will increase by 0.050. Okay, and then this divide by 1.0 plus V. Okay, and then I can just conveniently cancel out these two. Okay, and then after that 10 to the power minus 4.76. Okay, so this is equals to the concentration of H plus, and then of course I multiply by 0.450 divide by 0.550. Okay, and then from here I will determine the pH. So I'm going to take my calculator. Okay, so 0.45 divided by 0.55, that is 0.818. Okay, so 10 to the power 4.76, and then I divide the whole thing by this, and then I take the negative log to the base 10. I'm going to get 4.67. Okay, 4.67. Okay, so people, do you notice one thing? Despite having the same starting pH, okay, so let me highlight in pink. Okay, despite having the same starting pH of 4.76, okay, the buffer containing 0.500 moles per dm cube of ethanoic acid and ethanoate, okay, serves as a better buffer because at the end of the day, the reduction in pH is from 4.76 to 4.67. Okay, whereas on the other hand, when I start off my solution with concentration of ethanoic acid and ethanoate to be 0.2 moles per dm cube, the pH reduces from 4.76 to 4.24. Yeah, so therefore this explains why we have this last paragraph. The more concentrated the component of the buffer, the greater the buffer capacity. Okay, so I hope this particular examples helps you to recognize this. Yeah, so I repeat, despite having the same pH, starting pH, the buffer containing a greater concentration of the acid and the conjugate base, right, it will serve as a stronger buffer, okay, as compared to that with a lower concentration. Okay, then and you notice that over here, right, I'm only working with H plus. Okay, so what if I choose to add OH minus? Okay, so if I choose to add OH minus, I can confidently tell you that the pH for this particular buffer, maybe I will just call it buffer 2. Okay, so the pH of buffer 2, right, if I add in, if 0.050 moles of OH minus is added, okay, the pH will change from 4.76, so the change in pH from 4.76 to you notice the difference is 0.09, so it will change from 4.76 to 4.85. You notice that it's able to buffer similarly in both directions, because I have the same concentration of ethanoic acid ethanoate. Yeah, so basically I'm just playing around with this number, this particular number. So instead of 0.45 over 0.55, if I add OH minus, it will be 0.55 divided by 0.45. Yeah, so you'll go up the same units. Same case goes for this. So if for buffer 1, I add OH minus, the pH will increase from 4.76, okay, to, so it's a 0.52 units difference, right? So I'll just add 0.52, so that will be 5.28. Yeah. Then some of you might ask, what if I have a buffer solution where I have a little bit more acid and a little bit less salt? Yeah, so that means that the buffer with a heavier amount or higher amount of weak acid, right, will be able to buffer the addition of OH minus as compared to the addition of H plus, and vice versa. Yeah, so I hope you can get this logic. I will not go into further calculation examples for you. If you wish to, you can do on your own, or we can do it doing the tutorials, but I do hope when time permits, you can work on them yourself. Okay, so the most effective buffer is what we mentioned earlier on, the ratio of conjugate acid to base, or the ratio of the conjugate base to acid is 1:1. Okay, so this will be the most acidic buffer, and I hope you can understand why. And then so this particular buffer is said to have maximum buffer capacity. Okay, so the maximum buffer capacity tends to occur at the pH when it is the same as pKa for acidic buffer, and pOH equals to pKb for alkaline buffer. Right, and then some background information on effective buffer range. Okay, yeah, so we tend to give a ballpark figure for H2. So the effective buffer range would be from the ratio, let's say I have the acids and conjugates based. Okay, so a good figure to take note of will be from 10:1 ratio to all the way to 1:10. Okay, so therefore we're really looking at this region. The reason why we are looking at this region is because we want an effective buffer pH range to be within a certain range. Okay, so I think over here we are looking at pKa plus minus 1. Okay, so we don't want the pH to swing too much on the left and right. Okay, so that is something which you might want to be aware. Of course, these are just arbitrary numbers where analytical chemists come out with, and they feel that it is representative. Yeah, but depends on the industry you go into. Sometimes the buffer needs to satisfy a more stringent condition. Okay, so the next example we have, exercise is 4.5. So it reads, which of the following acids would be the best choice to combine with its sodium salt to make a solution buffer at pH 4.25. Okay, so my aim is to make a buffer of pH 4.25. So therefore, I need to choose an acid with a pK that is around there. I can't choose one that is very far away from that. Yeah, so in that case, ideally I should be choosing ethanoic acid, because it is, I mean, ethanoic acid in terms of pK, right, it is the closest to 4.25, and at the same time it also satisfies this particular condition where the pKa of the acid is plus minus 1 from the ideal buffer pH. Okay, so yeah, that will be the ideal choice. The rest will be very far away, and even if you manage to make a buffer out of it, it will not be an effective buffer, because you will have a lot more of one component as compared to the other. So for example, just an example, let's say if you want chlorous acid, the pK is 1.95. So if you want to make a buffer at 4.25, so that will mean that you will have a lot of the salts as compared to the chlorous acid, and that means it is much heavier. I mean, in terms of components, it will have a lot more ClO2 minus, the salts, chlorates, or per chloride, sorry, as compared to the acid itself. So that will not make it an effective buffer. Okay, so usually when it comes to MCQ questions, so it does help if you can just look at the numbers and then work them out directly. Okay, and of course the same goes for hypochlorous acid, 7.54, very far away from 4.25. Yeah, so it's almost impossible for you to make a buffer with a pH at 4.25. Okay. Then next we have the buffer system in blood. So those of you doing bio, or those of you are maybe a little bit familiar with how our blood work, you might have learned before in secondary school, is that it actually contains a large amount of the weak acid, which is carbonic acid, but it's actually existing in aqueous form, and its conjugate base known as bicarbonate or hydrogen carbonate if you look at the IUPAC naming system. So they help to maintain the pH of blood at about 7.4. Yeah. The reason why our blood needs to maintain a relatively constant pH is because most of the reaction taking place in our body will have its optimal range, or they prefer to work within a certain range, say between 6.8 to 7.8. Of course, again, these are all ballpark figures. There are the areas in the body where the enzymes work in extreme regions, but we don't deal with them. Okay, yeah. So I think over this portion, you were taught, you can read through on your own how the equilibrium operating between carbonic acid and bicarbonate helps to maintain the pH of the blood. Okay, yeah. So if not, you might want to go to the website to see how the pH regulation during exercise takes place if you want to. Okay, if not, then we will move on to exercise 4.6. Okay, so for 4.6, we were told that the main buffering agent in blood plasma is carbon dioxide hydrogen carbonate system. So hydrogen carbonate is the IUPAC name for bicarbonate. Yeah, so it will be good for you to know the different naming systems. So explain how the above system acts as a buffer when H plus and OH minus are added to the blood. Okay, so as I mentioned earlier on, it does help when you are able to write out a balance equation. So when H plus is added, you expect the hydrogen carbonates to react with the H plus, and in the process it gives you H2O and CO2. Okay, and when OH minus is added, you expect the CO2 to react with the OH minus, and in the course of the reaction you obtain hydrogen carbonate. Okay, and how do you explain how the above system acts as a buffer? So we explain it in a similar way as to how we explain how buffer system works in our earlier cases. So I think right now we will highlight the key component, which is bicarbonate and CO2. Okay, you can either represent the acid form as CO2, or you can simply use carbonic acid. So I will leave it up to you, because when you write the Ka expressions, you will be written as Ka is in this case concentration of H plus, concentration of HCO3 minus over H2CO3. Okay, so this will be a proxy to the CO2. And then so the focus in our explanation will be highlighting that the ratio of the bicarbonate and carbonic acid, if not you can say CO2 if you wish to, they remain relatively constant, because I have or the system has a large reservoir of these two species. Yeah, and because Ka is a temperature dependent variable, and I have a large reservoir of bicarbonate and carbonic acid, or CO2, the small amount of H plus and OH minus being added to the system, right, will not cause the ratio of bicarbonate to carbonic acid to change appreciably. So therefore H plus will remain relatively constant, pH remains relatively constant. So this is the usual flow in your answer. So I hope you can apply this to the system or to any of the questions which you are being asked to answer. Yeah, so answering question related to buffer need not be very complicated. It's actually quite straightforward if you understand the concepts behind. Okay, then for part B, you are told the pH of normal blood plasma is 7.4. Use the data above to calculate the ratio of bicarbonate to CO2. Hence, deduce whether blood has a greater capacity to absorb H plus or OH minus. Okay, so this is in response to what we are trying to answer to you earlier on, or trying to showcase to you earlier on. If you have the same amounts of acids and the conjugate base, then it can buffer well in both directions. But if you have more in one, then it will be able to buffer well in one particular direction. So that's why the question asks you to perform some calculation and then make your deduction from there. Okay, so yeah, so since we are given the pH of blood plasma to be 7.40, so we would simply use the Ka expression. So that's 7.90 times 10 to the power minus 7. I will equate it to the concentration of H plus. That will be 10 to the power minus 7.40, and then concentration of bicarbonates, and then concentration of CO2. Okay, so in this case, the ratio of bicarbonates to CO2 would be 19.8. So you notice that this actually falls outside the range what we mentioned. The ratio has either it's either 10 to 1 or all the way to 1 to 10, but 19.8 to 1, it's really out of the range. Yeah, but in this case, it works for blood. Yeah, because most of the reaction in our body produces H plus. Yeah, so our blood sort of evolved in a way so that it has a much greater capacity to absorb the H plus, because in this case, I have a lot more bicarbonate present in the blood. Yeah, so therefore our blood is better at absorbing H plus as compared to OH minus. Okay, so I hope from this question you get to see that the ratio 1 to 10 all the way to 10 to 1, right, is not a hard and fast rule. It's just a range where it's usually like that, but it's not always the case depending on the system. Okay, then for part C, using the above buffer system, explain briefly why strenuous exercise leads to an increase in rate of breathing. So when you when you're performing strenuous exercise, our body actually produces lactic acid. So the production of lactic acid, right? So in this case, strenuous exercise leads to the increase in amounts of lactic acids. Okay, so increase in amount of lactic acid will lead to an increase in the amount of H plus. Yeah, so the increase in amount of H plus will cause, okay, so I call it star, so will result in POE of the star to shift left. Okay, so when POE shift left, it results in an increase in the amount of CO2, and this will increase in our breathing rate so as to eliminate the CO2 produced. So because when our rates of breathing increase, right, it helps us to expel out the CO2. Okay, so that will be the answer to part C. I hope you can follow through this particular logic. Okay, moving on to section 5, we are looking at acid-base titrations. We will first look at the acid-base titration curve, which is a curve you obtain by plotting the pH against the volume of the titrant added. So it indicates and showcases to you how the pH changed during the titration. Usually the pH is measured using a pH meter, where you insert a pH probe in, and then you will be able to see the reading real time. Okay, so we will just go straight to the strong acid, strong base titration. Okay, so if I have 0.10 moles per dm cube of sodium hydroxide and I add it to 0.10 moles per dm cube of HCl, assume that I pipetted out 25 cubic centimeters of it, because given 25 cubic centimeters, right? So since we are looking at easy numbers like 0.10 and 0.10, you would expect the volume of sodium hydroxide I need for complete neutralization to be 25.0 as well. So the 25.0 is what we call the equivalence point. And from the graph, if you just extrapolate to the left hand side, you notice that the pH is 7. Okay, so it shouldn't come as a surprise, because if I have exactly a certain amount of HCl, which essentially is just H+, and then I add in the exact amount of OH- into the solution, I will not have any excess amount of H+ or OH-. And sodium chloride, it's being the salts of a strong acid and strong base, it wouldn't undergo hydrolysis. Yeah, so therefore the pH of the endpoints, essentially just sodium chloride solution, will be 7. Okay, so what are the feature of the titration curve? Well, the initial points is normally what we are interested in, so I will just put a pink over here. So this is what we call the initial pH. Yeah, you can easily calculate that based on some of the calculation we are familiar with earlier on. And because we know that the concentration is 0.10, you just take negative log base 10.1, sorry, not negative log base 10.1, you get 1. Okay, so this will be a relatively straightforward calculation. Okay, and you notice that the pH will increase gradually, but it's not a sharp increase. Okay, it is not a sharp increase because there is still a lot of H+ presence in the system. Yeah, so you notice that from just right before maybe 25, this whole region, right, the pH is about 2-ish, 2+. You can easily verify it for yourself. Even if I have, let's say 0.001 moles of H+ remaining in the solution of, let's say, 49 cubic centimeters, right, the pH will still be quite substantial. Yeah, so that explains why initially it doesn't change much. Okay, the major change will occur after I've added slight excess of OH-. Yeah, because when I've slight excess of OH-, right, the pH will shoot up, okay, until beyond 10+. Yeah, because a little bit amount of OH- in excess, right, yeah, when you calculate the pOH, I think the numbers will be quite substantial. And then once you calculate the pH out from there, it will be 10+, 11, 12. Okay, so that will be the characteristic of the titration curve. So you're going to have a gradual increase, but it will not be a very sharp increase. So you just go like this. And then once it's very near 25, then you need to draw a line that is very close to a vertical line. So you just shoot up. And then a bit more, then you'll hit the alkaline region. And then after that, you'll just go all the way. Even if you continue adding OH-, the pH will not change drastically. Again, for a very simple reason, because now the pH is simply dependent on the excess amount of OH- in the system. Okay, yeah. So most importantly, what you need to pay attention to for the pH titration curve for a strong acid and strong base is that I think number one, there is no buffer. I think very importantly, you need to know there is no buffer region or whatsoever. Number two is just a very boring curve where at the start, the increase is very gradual, and then towards the end point, it just shoot up vertically, and then after that, it will shoot up gradually, but it will not reach 14 anytime soon unless you reduce the volume drastically. Okay, so that's number one. And then number two is we need to decide on a suitable indicator for our titration. So essentially for strong acid, strong base titration, actually any indicator will do as long as the pKa falls within the region of rapid pH change. So the region of rapid pH change is actually over here. Yeah, so any indicator, for example, methyl orange pK is about 5, so 4-ish, 5, so methyl orange works. Phenolphthalein works as well, the working range 8 to 10. Yeah, so strong acid, strong base titration doesn't really matter which indicator you used. Yeah, but unfortunately, these two indicators have been phased out for use in school. The reason being they are found to be a little bit carcinogenic, so it's not advisable to use. So that's why in the lab, since JC1, you have been using thymobromo blue or thymothalin or something like that. Yeah, related indicators. But those are harder to observe. Okay, yeah. So the calculation, I think you can look at it over here. I think we have worked it out for you. So HCl strong acid dissociates completely. So this is what you get. And then half equivalence point. This half equivalence point, maybe you want to just pay attention to it. It is actually of no significance for strong acid, strong base. So maybe I just emphasize of no significance for strong acid, strong base titration. Okay, I think you guys need to pay attention to this. We are merely calculating it just for the sake of calculation, or just to impress upon you that the pH is very close to 1.00. Yeah, it has no significance. The significance will only come in when you're dealing with weak acid, strong base titration, or weak base, strong acid titration. So do take note of that. Okay, so right before the end point, which is 24.90, you can easily perform the calculation as well. You should get pH 3.70. Equivalence point pH will be 7, and then slightly after the equivalence point, you have excess OH minus. It shot up to 10.3, and then if I have 25.00 cubic centimeters in excess of OH minus, final pH will be 12.5. Okay, so from the earlier knowledge, you would be able to perform all these calculations at ease. Okay, I don't think it is of any difficulty. The only thing which you probably want to pay attention to is the fact that the total volume actually changes. Sometimes the students forgot that the total volume changes. Yeah, so if you forget that the total volume changes, sometimes you might not be able to get the correct answer. So just take note of it. Okay, yeah. Then if not, we'll move on to something that is very important for H2. That is weak acid, strong base titration. Okay, now even for weak acid, strong base titration, there will be two scenarios which you might be interested in. I think in the lecture notes, only one of the scenario is shown. So this particular scenario is when your ethanoic acid is being placed in the conical flask. Okay, so this is being placed in the conical flask. If you wish to, you can try to sketch the titration curve on your own. If sodium hydroxide is placed in the conical flask and ethanoic acid is placed in the burette. Okay, you can try to sketch the titration curve, and then also try to find out where is the buffer region, etc. But we will not go into this in our lecture notes. Yeah, I have already created another video for revision purposes, so if you wish to, you can just click on just right below the timestamps. I think I have given the link over there. Okay, but right now I'm just covering the basics. Yeah, so for the shape of the titration curve, it seems to be quite similar. I use the word seems to be, but you notice that the difference is at the start, right? There is a increase in the increase is quite sharp over here. Not very sharp, but quite sharp. And then after that is a gradual increase. Okay? And then after that it will shoot up just like a normal strong acid, strong base titration, and then after that you just move towards 12-ish, 13. Okay, so similar in shape. The difference is that for a strong acid, strong base titration, this portion is relatively flat. So if I just erase this, you should be able to tell. Yeah, this portion is the increase is the gradient is quite similar to the start. Yeah, but for weak acid, strong base titration, the increase is sharper at the beginning. Yeah, and the reason why after a while the increase isn't sharp is because you are actually producing a buffer here. Yeah, so remember, when you have pure ethanoic acid, once you have added sodium hydroxide, you are producing ethanoate. So a combination of a certain ratio of ethanoate and ethanoic acid is actually a buffer. So so of course the ideal maximum buffer capacity is about 4.76. So pKa plus minus 1, so that will be the ideal buffer region. Again, as I said, ideal. Just by textbook definitions. Okay, so in different situations, the ideal can be slightly different. Yeah, but what is more important is that for weak acid, strong base titration, the equivalence point is above 7. Okay, it's above 7. And I think you would have remembered what we mentioned earlier on. This is solely due to salt hydrolysis. So again, just a short revision. When ethanoic acid reacts with sodium hydroxide, it produces ethanoate, which is the conjugate base of ethanoic acids, and ethanoate itself undergoes partial hydrolysis to give you back ethanoic acid and an excess amount of OH minus. It is the excess amount of OH minus that contribute to the basicity of the salt solution. Yep. Okay, so I think I've mentioned enough of this, so let us just move on with this. So what are the features of the curve? Okay, so when no sodium hydroxide has been added, our initial pH is simply just calculating it based on what we know from simple acid-base equilibrium concepts. Okay, so we can do that quite easily. So we have ethanoic acids equilibrate partially in the presence of water to give us ethanoates and H3O plus. Okay, and then we can easily draft out an ice table. So initial concentration 0.10, so this is dash dash, and then minus x, so plus x plus x, so this will be 0.10 minus x, x. Okay, we can easily determine the Ka. K is given to us anyway, 1.8 times 10 to the power minus 5, so that will be x squared over 0.10 minus x. So again, we will make the assumption that x is much smaller than 0.10. Yep. So because of that, I can easily determine the H plus concentration, which is equals to x, and this is equals to the square root of 1.8 times 10 to the power minus 5 multiplied by 0.10. Okay, then once I've gotten the concentration of H plus, I can determine the pH to be 2.87. Yeah, so I think most of you should be quite familiar with this kind of calculation right now. Yeah, after going through some of the earlier sections. And then between the volume of sodium hydroxide between 0 to 25, it will just increase gradually. Okay, as what we mentioned here. So the increase is a little bit sharp at the beginning, but after that is a gradual increase because, again, we are producing more and more buffer. Sorry, we are producing more and more ethanoate. So the combination of ethanoate and ethanoic acid is a buffer itself. Okay, so right now we are going to perform a calculation involving the pH when the sodium hydroxide added is 12.50. This is otherwise known as the half equivalence point as well. Okay, this has significance. Okay, the one involving strong acid, strong base has no significance. Okay, so we can easily do this because we can easily determine the amount of sodium hydroxide added. So that will be 0.0125 multiplied by the concentration of hydroxide is 0.1, I think. Yes, so multiplied by 0.10. Yeah, so that will be this I'm going to write in standard forms, 1.25 times 10 to the power minus 3 moles. Okay, so the initial amount of ethanoic acid will be 2.5 times 10 to the power of minus 3. So that will be 0.0250 times 0.10. So that will be 2.50 times 10 to the power minus 3 moles. So you notice that when I add in 1.25 times 10 to the power minus 3 moles of sodium hydroxide, the number of moles of ethanoate produced will therefore be 1.25 times 10 to the power minus 3 moles. And this will also be the amount of ethanoic acid remaining. Okay, and because of that, I can easily determine the concentration of H+, or rather I can write out the K expression. So that will be Ka equals to the concentration of H+, multiplied by the concentration of ethanoates, CH3CO2 minus, and then divide by the concentration of ethanoic acid. And because the number of moles of ethanoic acid and ethanoates are the same, these two can be cancelled away. Okay, so therefore pH equals to pKa, which is equals to 4.74 in this case. Okay, yep, so I hope you can easily obtain this particular calculation, and this is actually to answer this portion where the maximum buffer capacity occurs when half of it reacted, and then pH is equals to pKa. Okay, then moving on, we'll move on to the next portion when the volume of sodium hydroxide added is 25.00. Okay, the pH is expected to be above 7, but what is the exact pH? That is where we need to perform the relevant calculation. Okay, so you notice that I'm using sodium hydroxide and ethanoic acid with the same concentration of 0.10. Yeah, so therefore the volume of sodium hydroxide I need for complete neutralization will be 25.00. So I think from here I can easily determine the total volume. So the total volume at the end of the day is 50.00 cubic centimeters, or you can write it in terms of dm cube will be 0.050 dm cube. Okay, then the number of moles of ethanoates I have in the system will be the same as the amount of ethanoic acid I have in the beginning. Okay, so that will be what we have written earlier on, 2.50 times 10 to the power minus 3 moles. So therefore, the concentration of ethanoates in the new total in the new total volume, it will be 2.50 times 10 to the power minus 3 divided by 0.050. Okay, this will give us 0.0500 moles per dm cube. Yeah, for students who are sharp enough, you notice that since the initial concentration is 0.1 and volume doubles, so concentration will half, so you can easily get 0.0500 as well, but I'm just showing you the calculation here for completion purposes. Okay, then after that, I think from here you can easily work out using another ice table if you wish to. So I'm going to focus on this particular equation. Okay, so for this particular equation, it represents the salt hydrolysis of ethanoates. So with H2O equilibrate to give us ethanoic acids and OH minus. I am defining Kb over here. So with an ice table, the initial concentration of ethanoate is 0.050. So dash dash dash. Then after that, minus Y, because this will be the amount which ionizes, or the concentration which ionizes. So equilibrium concentration will be 0.050 minus Y, and then Y. Okay, and then here I'm defining Kb to be Y squared over 0.050 minus Y. And I can easily determine Kb to be 10 to the power minus 14 divided by the Ka, which is given to me as 1.8 times 10 to the power minus 5. Okay, so again, I need to assume that the amount which ionizes is really small. So assume that y is much smaller than 0.050. Okay, so from here I will be able to determine y, which essentially is the concentration of OH minus, and then just punch your calculators, because you know this value, you know this, and you assume y is very, very small. So the denominator becomes 0.050, and then once you punch the calculator, you should be able to get 5.27 times 10 to the power of minus 6 moles per dm cube. And then from here I can determine POH to be, just punch the calculator, just give me a while, minus log base 10, 5.27 times 10 to the power of minus 6. Okay, I will be able to get 5.28. 5.28. So therefore pH is equals to 8.72. Okay, so indeed it is above 7. Yep. So the most important thing when you are performing calculation involving salt hydrolysis is to take note of the change in the total volume. Most of our students who got this part wrong comes from various reasons. I think one of them is they forgot to consider the total volume. Next, they did not calculate KB correctly. Okay, usually that's about it. Okay, if you can get some of these things right, I think it is very difficult to get the question wrong. Okay, then what about excess amount of sodium hydroxide being added? So let's say the volume of sodium hydroxide added is now 30.00 cubic centimeters. Then what's going to happen? Okay, so 30.00 cubic centimeters will mean that the amount of sodium hydroxide added in excess is 5.00 cubic centimeters. So the first thing I need to determine is the amount of OH minus in excess. And this is not too difficult to calculate, because it is simply 0.0050 times 0.10. So I'm going to get 5.00 times 10 to the power minus 4 moles. And this number, right, is likely to be much greater. So this number is likely to be greater than the amount of OH minus due to hydrolysis of ethanoates. Yeah, so therefore when we calculate the pH of the final solution, when we added sodium hydroxide in excess, we will not consider the contribution of the OH minus from the salt hydrolysis. Yeah, anyway, you should also be aware that the artificial addition of OH minus will actually suppress the ionization of ethanoates. So it will push the position of equilibrium to the left. Yeah, so in this case, I think this assumption is valid over here, that we do not need to artificially add in the amounts of OH minus contributed from the salt hydrolysis. So you have to remember that, because this is often the misconception that which students might have. Okay, so the final concentration of OH minus will be 5.00 times 10 to the power minus 4 divided by the total volume, essentially 0.0550. So I'm going to get 9.09 times 10 to the power minus 3 moles per dm cube. From here I can calculate POH to be 2.04, and pH is therefore 12.0. Okay, yeah, so I hope after performing all these calculations, you are quite familiar with the calculation of the various point of titration curve. Okay, so if you watch the videos which I've uploaded regarding calculation of the main points in a titration curve, so I can just summarize it over here. So while there are 4 main points we wish to calculate in our titration curve, but you don't have to calculate for all the points at any one point in time, depending on the question. The first is the initial pH. Next will be the pH at the half equivalence point, and then the pH at the equivalence point, and then the pH when a slight excess of OH minus is added. Okay, it need not be 30, it can be any value, it can be 26, or it can be 40, it doesn't really matter. Okay, so once you are able to calculate the pH of all these 4 regions confidently, then I would say your understanding of acid-base equilibrium will be very strong, and you will not have any major problems in questions related to acid-base. So you don't really need to worry about that. Yeah, but not to worry. I know some of you are maybe a little bit confused. Yeah, but as long as you continue to try hard and work through your tutorials and some of the extra questions we give you in the tutorials or during lectures, I think that will be fine. Okay, yeah. Then okay, so right now we have a strong acid and a weak base titration. So over here we are adding aqueous ammonia to a strong acid. So the strong acid is hydrochloric acid. Okay, so this is a little bit different. The reason why this is a little bit different is that my hydrochloric acid is in the conical flask. Okay, so that is something you need to take note of. So this is in the conical flask. And because hydrochloric acid is in the conical flask, the first portion of your titration curve, right, is actually very similar to a strong acid, strong base titration, and you are not producing any buffer. Okay, so no buffer here. Okay, you might be wondering how come the buffer becomes at the other region. Okay, the reason is in your conical flask, right, what you have is a strong acid. So whenever you add in aqueous ammonia, the ammonia will completely react with the strong acid to give you ammonium. So over here, you are producing ammonium. So there is no ammonia present because any ammonia you have added would have reacted with the H+. Yeah, and you need a combination of ammonium and ammonia to produce a buffer. So there is no buffer at the beginning. The buffer is only produced after the equivalence point, because after the equivalence point, right, any ammonia added, okay, the combination of ammonia and ammonium will have contribute to a region of buffer or a buffering region. As to where is the ideal buffering region, yeah, so this is no longer called half equivalence point. It's essentially the equivalence point times 2. So this will be the ideal maximum buffer capacity. Yeah, and the reason why this is the case is because if you try to perform a simple calculation, up to the equivalence point, what is the amount of ammonium produced? And what is the amount of ammonia you need to add in order to have the same amount as the ammonium produced at the equivalence point? So in that case, the answer will be twice this volume. Yeah, so that is why the buffer region is over here. Okay, so again, if you are in doubt, you need to maybe think through a little bit about what exactly is going on, and then do raise questions in the tutorials. Okay, so the features of this curve will be initial pH. I think this is straightforward, just minus log base 10 of 0.1, and then anything in between, we are not going to calculate any buffering region. I mean, you can calculate the pH if you want, but it's not very significant. There's no significant change. The main pH here is due to the concentration of the excess H+. At the equivalence point, of course, we are interested in calculating, because this will be due to the partial ionization of ammonium. And then, of course, anything in excess, which is beyond the equivalence point, will be a combination of the conjugate acid, which is ammonium form, and the amounts of ammonia in excess. So this particular combination will give rise to a buffer solution. Okay, so we have exercise 5.1 over here. So I think they needed you to perform some calculations. So with reference to the above examples, determine the pH of the solution in the conical flask when 12.50 cubic centimeters of ammonia has been added. Then they ask you what is the volume of ammonia added when maximum buffer capacity occurs, and what is the pH at this point. Okay, so we can easily calculate this. So when 12.50 of ammonia has been added, all the ammonia added would have reacted with H plus to give us ammonium. So the amounts of H plus remaining would then be equals to 0.025 minus, oh sorry, not minus, multiply by 0.10, so that's the concentration, minus 0.0125 multiplied by 0.10. So over here, the amount of H plus remaining would be 1.25 times 10 to the power of minus 3 moles. Okay, some of you might be wondering, what about the ionization of ammonium? So the ionization of ammonium okay, actually it's given here, so I'll just use this. Okay, so we are talking about the ionization of ammonium to give us ammonia. Well, I have relatively a huge amount of H plus present. So the presence of H plus will suppress the ionization of ammonium. So your ammonium will probably not ionize much. Yeah, so therefore the concentration of H plus is solely due to this amount of H plus present. Okay, so therefore pH will simply be minus log base 10 of this amount of H plus. So minus log to the base 10. 1.25 times 10 to the power minus 3 divided by the total volume, which is 0.025 plus 0.0125. Okay, so I should be able to get 1.48. Again, this value has not much significance, so do not be bothered by half equivalence point if that particular equivalence point is not a buffer. Yeah, so there's no point in looking at it when it's not a buffer. And then what is the volume of ammonia added when maximum buffer capacity occurs? So I think I briefly run you through the thought process just now. You can determine by looking at the amount of ammonium being formed when 25.0 cubic centimeters of ammonia has been added. So that essentially is 0.025 multiplied by 0.10. So that will be 2.50 times 10 to the power minus 3 moles. Okay, so if I want to achieve maximum buffer capacity, I need to add in the same amount of aqueous ammonia. Okay, so I need to add in the same amount of aqueous ammonia in order to produce the maximum buffer capacity. So in order to add in the same amount of aqueous ammonia, this will have to be 2.50 times 10 to the power minus 3 moles. And then from here, the volume of ammonia will therefore be 25.0 cubic centimeters. Okay, and the total volume involved after adding 25.0 will be 25.0 plus the initial amount of ammonia which I've added. So that will be 25.0 plus 25.0, and I will get 50.0. Yeah, so I think this question might not be so clear. What it wants to say is, what is the total volume of ammonia I need to add from the start, not after the equivalence point. Okay, so from the start, I will add 25 to reach the equivalence point, a further 25 to reach the maximum buffer capacity, so the total volume is 50.00. And then the pH at this point, again, I have the same amounts of ammonium and ammonia. So therefore, we are looking at Kb of ammonium, of OH minus, ammonium, and ammonia. And because these two are the same, so it will cancel out. Okay, so once these two cancel out, I'm going to get POH equals to PKB, and KB is given to be 1.8 times 10 to the power minus 5. Okay, so from here, you can get 4.74. Then I'm going to get pH to be 9.26. Okay, yeah, so I think I just hope that you find the calculation not too daunting, because the calculation itself is actually quite straightforward if you are very sharp in determining which species reacts with which species. Yeah, usually the difficulty comes in when you are confused between whether you should be using Ka or Kb, or when you get mixed up with the total volume. Okay, then next we'll move on to weak acid, weak base titration. Over here we have our weak base, which is aqueous ammonia in the burettes, and then we have our weak acid, ethanoic acid, in the conical flask. Okay, so you notice the shape of the titration curve is unlike the earlier examples of weak base strong acid titration, where the equivalence points, where the change in the pH at the equivalence point is very sharp. It's a vertical increase. Okay, so let us just move back to the weak acid strong base titration. Again, this portion is very sharp, and strong acid strong base titration, the change in pH at the equivalence point is also very sharp. But for a weak base weak acid titration, you notice that at the equivalence point, the change in pH is not sharp. In fact, the gradient just go from gentle to steep, and then go back to gentle again. Yeah, so you might realize that because of this particular characteristic, it is difficult to perform such a titration using an indicator. Yeah, because if we were to use phenolphthalein, there is no region or there's any rapid pH change which coincide with the working range of phenolphthalein. Okay, same case goes for methyl orange. Yep, and then okay, so I think what I mentioned earlier on is stated over here. There is no sharp change in pH, so no suitable indicator can be used, but we can still use a pH meter. The reason why we can use a pH meter is obviously because you know the initial amounts of ethanoic acid I have. So if I know the initial amount of ethanoic acid I have, I will be able to determine the volume of ammonia to reach the equivalence points. Okay, and I'm able to plot out a graph which looks something like this. So I can roughly tell that, okay, around this region will be the equivalence point. But for a weak acid, weak base titration, in our case, you are not able to use any suitable indicator to determine the endpoints. So you can only use a pH meter to help you. And if you are already thinking one or two steps ahead, I think you can explain why the titration curve is of this particular shape. Well, because if we have a weak acid and a weak base, in the course of the titration, let's say we started off with the weak acid, in this case ethanoic acid. In the course of titration, I am producing ethanoic, which itself is also a weak base. And then as my weak base reacts with ethanoic acid, it will produce the conjugate acid, ammonium, which itself is also a weak acid. So in this case, the titrant and whatever I'm reacting with the titrant, in this case ethanoic acid, they buffer each other. So that explains why there is no clear change in the pH as the reaction proceeds, especially at the equivalence points. Okay, then with that, we will move on to the titration curve involving polyprotic acids. Yep. If I'm to move back to this a little bit, right, you might be wondering whether such a question will be tested in exams, etc. You notice that we didn't focus too much on it. In fact, not much calculation can be done except, unless you know the systematic treatment of equilibrium, which we will not discuss too much for H2. Yeah, so because of that, I don't think you will expect many of such questions to come up for assessment, except maybe to explain why a suitable indicator is not possible, or why there isn't a sharp change in pH, which I think the reasons I gave earlier on. Okay, then for titration curve involving polyprotic acids and bases, what exactly are polyprotic acids? So for example, in this case, we have sulfurous acids, which have two Kas, because it have two equivalent of H+. So the first ionization will produce HSO3 minus and H3O plus. You notice the Ka value, the magnitude is in the region of 10 to the power minus 2. For the second ionization, you notice that HSO3 minus is 1 million times weaker than H2SO3, okay, as seen from the Ka2 value. And this is often the case, and I don't think it's anything out of the blue, because when we start off with H2SO3, right, you notice that it's a neutral species, and as it ionizes, it becomes HSO3 minus and H3O plus. Okay, so it goes from neutral species to a species with -1 charge. But for HSO3 minus itself is a negatively charged species. So for it to eject out a proton and at the same time doubling its charge, I think thermodynamically it is more challenging. So because of that, you expect in most cases the subsequent Ka value to be significantly lower than the first Ka values. Okay, then from the titration curve, because we are titrating against sodium hydroxide, you notice that there will be 2 equivalence points. Okay, so because we are using the same concentration, I supposed, so the volume needed will go from 25 to 50.0. Okay, so if we are to plot out a titration curve, we can easily determine the volume I need to reach the first equivalence point as well as the second equivalence point. Okay, however, based on your understanding, you are not able to determine the pH of the first equivalence point, or rather after the first equivalence point. The reason is the HSO3 minus, right, itself is also an acid. Okay, so HSO3 minus will, has a dual role here. So first, it will ionize to give us SO3 2 minus and H3O plus. Okay, at the same time, it will also undergo partial hydrolysis in water to give us back H2SO3 and OH minus. So a proper calculation requires you to take into consideration both of this reaction in order to calculate the final pH, which you are not equipped with at this stage. Okay, so in that case, most of the time we will not ask you to calculate the pH of the first equivalent point. Okay, but if you want to read more, you can go and explore more about systematic treatment of equilibrium, etc. But I can show you an approximate way to determine the pH at the equivalence point over here. Okay, before that, we need to calculate the pKa's. Okay, so pKa1 essentially is minus log base 10 of 1.4 times 10 to the power minus 2. Okay, so we are getting 1.85. pKa2 minus log base 10, 6.5 times 10 to the power of minus 8. We are getting 7.19. Okay, so pKa2 equals to 7.19. From the titration curve, we are able to indicate 2 important points. Okay, so that is the first half equivalence points. Okay, so this pH, you can write it as 1.85. Okay, so this will be 1.85. The second equivalence point will be 12.5 plus 25, so that will be 37.5. So you should be able to write it as 7.19. Okay, so if you read in advance a little bit, the pH of this equivalence point, you can approximate it to be half of 7.19 and 1.85. So that will be 7.19, so 1.85 plus 7.19 divided by 2. So it will be approximately 4.52. Okay, but this is not required in your syllabus, so remember this. So don't be too stressed over this. Okay, so not required in the syllabus. Yeah, but it is required, or rather you are required to know how to calculate the pH of the endpoint, which is after the second equivalence point. And this shouldn't come as a surprise, because you work out you will work it out in the same way as how you work out the pH of the equivalence point for a weak acid strong base titration. Okay, using this similar method. Okay, so however, you need to choose the correct pKa associated with SO32 minus. So you should be choosing pKa2, okay, and therefore you need to calculate this pH by looking at the correct pKb1. Essentially is 14 minus 7.19, which is 6.81. So make sure you choose the correct pKb1. If you choose the other one, then you won't be able to get the correct answer. Okay, so I hope that is clear cut for you. I think I've mentioned a little bit more than what you need to know. So you can just read through the rest of the notes. Okay, so to further assimilate some of the understanding lah. Is it possible for us to determine the two equivalence point without using the pH meter? Can we do titration using indicator? Yes, you can. You just need to know the indicator which is able to have rapid pH change at around this region, and another indicator with rapid pH change at a region in the alkaline region. So this is what we normally call a double indicator experiment. So in this case, in the past, usually we use methyl orange followed by phenolphthalein. But right now, I think we can have some different combination depending on what's available in the lab. Okay, so over here we also have a titration of sodium carbonate with hydrochloric acid. Yeah, so you can see that in the course of the reaction, you are producing two buffer regions. So this buffer region contains carbonate and bicarbonate, and then the other buffer region contains bicarbonate and carbonic acid in the form of CO2. Okay, so in this case, the first rapid pH change, actually not so rapid, about 8.5. The next one about 3.5. So in this case, suitable indicator phenolphthalein. The other one will be methyl orange. Okay, so double indicator experiment quite common in the lab. So you will be given enough exposure to work on them. Okay. Yep. If not, let us work on exercise 5.2. I have 25.0 cubic centimeters of a solution containing sodium carbonate and sodium hydrogen carbonate. Okay, so I have a combination of these two. Let me write out the formula first. CO3 minus. Okay, and needed 22.50 cubic centimeters of hydrochloric acid of a certain concentration to decolorize phenolphthalein. Okay, so based on the titration curve above, to decolorize phenolphthalein, I am producing bicarbonate. Yeah, so you can straight away tell that this is the volume of hydrochloric acid I need to react away all the carbonates. Yeah, so from here we can write this out clearly. So number of moles of HCl needed to react away all carbonates. All carbonates will be equals to 0.0225. Oh, sorry, the pen is not working very well. Okay, so 0.0225 multiplied by 0.100. So I'm going to get 2.25 times 10 to the power minus 3 moles. And this is also the number of moles of carbonates present. Okay, so I'm required to calculate the concentration of sodium carbonate. So therefore, concentration of sodium carbonate will therefore be 2.25 times 10 to the power minus 3 divided by 0.025. Okay, so that will give me 0.0900 moles per dm cube. Okay, then next, on addition of methyl orange, a further 28.50 cubic centimeters of the acid was needed to turn the indicator orange. Yeah, so This 28.50 moles of hydrochloric acid reacted with all the hydrogen carbonate present. And this hydrogen carbonate comes from two sources. The first source is from the original amount of hydrogen carbonate in the system, which is over here. Okay, the second source comes from the hydrogen carbonate produced from the reaction with the 22.50 cubic centimeters of HCl. So we need to know how to differentiate between the two. Okay, but nonetheless, we'll just keep our calculation simple and straightforward. So we'll just find out the number of moles of HCl needed to react with all the bicarbonates present. Okay, so that will be equals to 0.0285 multiplied by 0.100. So that will give me 2.85 times 10 to the power of minus 3 moles. Okay, but again, I mentioned the bicarbonates comes from two sources. So I need to find out the number of moles of bicarbonate originally present. Okay, so that will be 2.85 times 10 to the power of minus 3. I need to minus it away from those that are produced from the reaction with carbonate. So this will be 2.25 times 10 to the power minus 3. Okay, so from here I will get 6.00 times 10 to the power minus 4 moles. Okay, so therefore the concentration of bicarbonate will then be equals to 6.00 times 10 to the power minus 4 divided by 0.025. Okay, then I will get 0.0240 moles per dm cube of sodium hydrogen carbonate in the original solution. Okay, so I hope you are okay with such stoichiometry calculation, and it's not too daunting. Okay, so with that we'll move on to acid-base indicators. So do take note, the most important idea for acid-base indicators, whether we are talking about methyl orange, phenolphthalein, etc., right, they are all weak acids themselves. So in different forms, either in their original acid form or in their conjugate base form. Okay, so for example, this is the background given to you. So for litmus, we are looking at the red form is like this, and then the blue form. Phenolphthalein is colorless, and then it's pink like this, methyl orange, and then yellow like this. You notice that when it is colored, there tends to be an extended conjugation. What do I mean by extended conjugation? So the structures tend to be flat. Although you don't really need to know this for H2, but I thought it's good to be aware of it. So you can see that this portion is flat. So there's some form of extended conjugation. Okay, like for example, when it's pink, the extended conjugation goes from here to here, and then in this case it goes from here all the way to the end. Okay, yeah, but this is not required for your complete understanding for H2, so I don't think you need to be too worried about that. If you are really interested, you can read more about it, and then I think you will gain a lot more. But if not, you can ask me for discussion during tutorials. Okay, then yeah, so for litmus, when concentration of H+ is high, the POE will shift to the left, so you get the red form. Okay, so this is the red form that you get. So this is the red form. Then when the concentration of H+ is low, I will get the blue form, which is where OH minus, where H+ will be reacted away. So I'm going to get this blue form. Okay, then I think that's about it. Working range of indicators is also important. So generally we are looking at the equilibrium constant of the indicator between the conjugate base and its acids. Okay, so we are really looking at pK indicator plus minus 1. Okay, so in general, the working range of the indicator is pK indicator plus minus 1. I think you can read through the details. These are just some common indicators you need to know. Do you really need to memorize the color? Probably no, but some of them you'll be familiar with from the lab. Okay, so for example, thymo blue, I think you have used that in the lab before. So it goes from yellow to green at the equivalence point. If you exceed, you will reach blue. And then thymothalin, it's colorless, and then you get some light blue, and then endpoint will be blue. Okay, so these are the alternatives to phenolphthalein. Bromo-thymo blue is also commonly used. So yellow in acidic region, endpoint would be green, and then once it exceeded the endpoint, you will get the blue color. Okay, yeah. So that is something you might want to take note of. And again, some of the students will get a bit confused by the terms over here when we mean color in basic and acidic region, because the working range for, let's say for methyl orange, right, the working range is from 3.1 to 4.4. So for it to turn yellow, actually anything above 4.4 will do. So, but 4.4 is not exactly in the basic region. So how do we qualify that? So in general, when we say basic region, of course, we refer to above 7, but we also need to correspond it with the pH working range in order to determine the main species involved. Yeah, so these words, when we say acidic region, basic region, they are just generic. So they do not really mean that it has to be very acidic or very basic. Yeah, so it really depends on the structure of the indicators. Okay, so again, when you're in doubt, do clarify in the tutorials. Okay, so for exercise 5.3, at low pH, the color of bromocresol green is yellow. So at high pH, the color is blue. Okay, so you are supposed to calculate the pH range at which the color of bromocresol green is green. Okay, so again, what we can do here is we are given the K of the indicator. Okay, so remember the working range of the indicator is of a certain value. So what we can do now is we can write K of indicator. This would be H plus an indicator divide by H of the indicator. Okay, and then what we can do here is we know the equilibrium constant of the indicator, which is 1.58 times 10 to the power minus 5. Okay, and let's see what we can do from here. So we can just sub in the values. 1.58 times 10 to the power minus 5 equals to concentration of H plus, concentration of indicator, and then H of the indicator. Okay, so we do understand that the ratio of indicator to H indicator has two extreme range. One of it is 0.1, and the other extreme end is actually 10. Okay, so what we can do is just to substitute this into this, and then we can calculate the first pH. Okay, so therefore, where I'm just going to write it here. So when the ratio of indicator to HIN, or IN minus to HIN is 0.1, what pH am I getting? So what I'm going to do now is simply 1.58 times 10 to the power minus 5 divided by 0.1, and then I'm going to take a negative log base 10 of this. I'm getting 3.80. So this is 3.80. Okay, so the other extreme, the pH, if I just punch my calculator, I should get 5.80. Yeah, so therefore the working range of the indicator will be from 3.80 to 5.80. Okay, so I hope that makes a bit of sense to you, and it does give you a better gauge and perhaps slightly better understanding on the nature of indicators. Okay, so if we move on to 5.4 on the choices of indicators, at the end of the day, the same point still applies. We are going to choose an indicator where the working range coincides with the region of rapid pH change, and this is usually near the equivalence point. Okay, and this region of rapid pH change really depends on the nature of the acid and alkali combined as well. So in general, when we are dealing with strong acid, strong alkali, or strong base titration, most of the indicators work relatively well. So whether we are talking about methyl orange, phenolphthalein, thymol-blue, if we have strong acid, weak base titration, the end point or the equivalence point will be less than 7. So we'll be using an indicator with a working range below 7. So that will be methyl orange. Okay. For weak acid, strong base titration, we are looking at an indicator above 7 for its working range. So that would be phenolphthalein or thymol-blue. You can easily get the values from here. Okay, so generally, these are good for strong base weak acid titration. These are good for strong acid weak base titration. Okay, and usually strong acid, strong base titration, most of the indicators will work generally well. Yeah, so it's really your choice and your call. Okay, but as what we have seen earlier on, for weak acid, weak alkali titration, there is no suitable indicator because for weak acid and weak base titration, there isn't really a region of rapid pH change, so it's difficult to use an indicator to help you in your titration. Okay, so using a pH meter and plotting the values real time might help better. Yeah. Then finally, we're going to move on to exercise 5.4. So we have a 25.0 cubic centimeter solution containing a certain concentration of lactic acid. I titrate it with sodium hydroxide of this particular concentration. pH equivalence point is 8.29. The table below lists the working range of some acid-base indicators. Comment on whether each of the following indicators can be used. Okay, so this is an example of a weak acid, strong base titration. So equivalence point is above 7. Okay, so because it's a weak acid, strong base titration, and if you look at the working range, for bromothymol-blue, it doesn't coincide. Okay, so no good. Methyl orange doesn't coincide as well, so no good. Neutral red doesn't coincide, so no good. Okay, thymol-blue is fine. Okay, so it's actually okay. Naphthophthalein is okay also because it coincides with the equivalence point, so this is okay. And then thymolphthalein in fact is not suitable because if you look at the region, it is actually above, so not suitable. So the only suitable indicator will be thymol-blue and naphthophthalein. Okay, so remember, at the end of the day, how do you choose the indicator? You just need to make sure that the working range coincides with the region of rapid pH change. And it is important to look at the pH of the equivalence point, 8.29, and you will roughly be able to guess the region of rapid pH change, probably about 7-ish, 6-ish to about, say, 10-ish. Yeah. Okay, so I think that will be okay. So other than that, I think if you have more questions, please do clarify in the tutorials. And then when we have the planning questions involving acid-base equilibria, I think it is good for you to look at the examples from the Google site. So please go to the Google site and look at the relevant two examples, which I think they will help you to firm up your understanding. These are from our blog tests. So an example of acid-base planning questions, which determination of pK of a weak acid or a weak base, and then preparation of a specific buffer. Okay, and moving forwards, this concept will help you in firming up and strengthening your understanding when we go into organic chemistry, especially so when we are dealing with weak organic acids such as phenol, ethanoic acid, and even weak bases such as amines. And then in transition metal chemistry, you will be dealing with salt hydrolysis due to cations, which will also be related to QA. Okay, so do take note of these chapters. And then the final page, we have a summary of the concepts and which you need to be aware of, and the application. Again, I want to stress that you should not be memorizing any of these equations. All the concepts you need, you have already learned them in chemical equilibrium. Okay, what you should be focusing on is the application of chemical equilibrium concepts to help you to perform the necessary calculation in acid-base equilibrium. Okay, so with that, we have come to the end of the acid-base equilibrium lecture, and do look forward to future videos which will be discussing on other topics.